A gap coupled microstrip resonator. In the previous video, we have studied different configurations for uh, excitation of resonators. One of these excitation methods is gap coupled to microstrip. In this case, we said that we have a microstrip line coupled to a printed microstrip resonators, and is coupled through a capacitive coupling at this gap. Assuming that we have an open circuit microstrip line resonator of length lambda over 2, which have an input impedance equals minus jz naught cotan beta L, and beta L in this case is pi, so cotan pi is infinity, and this corresponds to parallel RLC circuit or parallel RLC resonant circuit. Now, assuming that we are going to excite this lambda over 2 open circuit transmission line to a feeding microstrip line through this gap, we have the equivalent circuit looks like this. Here is the feeding transmission line of characteristic impedance Z0, and here is the equivalent capacitance of the gap, and this is the open circuited resonator of length L, and the length here is lambda over 2. The input impedance of this combination here, Z input, would be the input impedance of this capacitor in series with the input impedance of this resonator. As I mentioned, the input impedance of this open circuit transmission line resonator is minus J Z naught cotan beta L. So the total input impedance in this case is the input impedance of the capacitor, which is minus J over omega C, plus the input impedance of this resonator, which is minus Jz naught cotan beta A. If we are going to normalize the input impedance, so the normalized input impedance small z is the input impedance Z over Z naught, which is minus J of 1 multiplied by 1 over omega C plus Z naught cotan beta L. All of this stuff is over Z naught. This actually the input impedance seen by the feeding transmission line. We can rearrange this input impedance by multiplying both the numerator and the denominator by tan beta L, and also multiplying both the numerator and the denominator by Z naught omega C. So, multiplying the numerator and the denominator by omega C. So, in this case, the normalized input impedance can be simply formed as minus J multiplied by tan beta L plus Z naught multiplied by omega C over tan beta L multiplied by Z naught multiplied by omega C. We are going to name that Z naught multiplied by omega C as BC. Okay? So, the normalized input impedance is minus J multiplied by tan beta L plus BC over BC tan beta L. Effectively, When the resonator was open circuit transmission line, we were looking for the roots of the cotan beta L. And the roots of the cotan beta L in this case correspond to the resonance of parallel RLC circuit. However, when we connect this open circuit resonator through the capacitor or the equivalent capacitance to the feeding transmission line, we are looking now for the resonance of the normalized impedance small z when the numerator equals 0. So, assuming that, for example, the value of the capacitance is infinity, such that the value of the capacitance is very small, we are looking for nearly tan beta L equals 0, not cotan beta L equals 0. We are now actually looking for the condition for the resonance that tan beta L plus BC equals 0. This corresponds to series RLC circuit, not parallel LC circuit. So, it should be noted here that connecting a parallel RLC circuit through a capacitor to the feeding or the excitation line will convert the type of the resonance circuit from parallel LC circuit to series LC circuit. Okay? Actually, this condition of resonance can be solved graphically as we can plot the value of tan beta L as a function of beta L, and on the other hand we can draw the value of BC, which equal Z naught omega C as a function of omega. And because we are looking for tan beta L equals minus beta BC, we are going to draw minus BC. Then the intersection between the curve of tan beta L and the line corresponds to minus BC will correspond to the resonant frequency in this case. And because the value of the capacitance is usually very small in this case, the resonant frequency would be quite close to the value beta L equals pi, or in other words, L equals lambda over 2. So we say that if the value of BC is much smaller than unity, or in other words, the value of the capacitance is very small, the resonant frequency will be very close to beta L equal pi. As a comments on the gap coupled microstrip resonator, should be noted that the uncoupled lambda over 2 open circuit transmission line resonator looks like a parallel RLC circuit near the resonance. But the present case for capacitive coupled lambda over 2 resonator looks like a series RLC circuit near the resonance, because near lambda over 2 the input impedance is nearly 0, not infinity. This is because the series coupling capacitor has the effect of inverting the driving point of impedance of the resonator. Actually, this inversion will be deeply studied in Chapter 8 in studying the filters. Alright? Now, let us return back to the normalized input impedance. The normalized input impedance, as we said, can be represented as minus J tan beta L plus BC over BC multiplied by tan beta L. The question now, what will be the input impedance or the normalized input impedance close to the resonant frequency? This can be obtained by expanding this normalized impedance as a function of omega in Taylor series. So Z as a function of omega equals Z at omega 1, which is the input impedance at the resonance, plus omega minus omega 1 multiplied by dz of omega by d omega at omega equals omega 1 plus omega minus omega 1 squared over 2 multiplied by d2 of z or d squared of z by d omega squared at omega equals omega 1 and so on. This is actually Taylor series representation of the function z as a function of omega. But we know that the resonance condition occurs when the value of z equals 0. This means that z at the omega 1 or z at omega 1 or z at the resonant frequency, this term is 0. So actually we are starting from the first derivative. Here the normalized impedance is actually represented in terms of beta L, not in terms of omega. So instead of taking the derivation with respect to omega, we can take the derivation with respect to beta L. Then we multiply by d beta L by d omega. So we can rearrange this term as omega minus omega 1 multiplied by dz by d beta L multiplied by d beta L over d omega at omega 1 plus the higher order terms. We are going to take into consideration only the first derivative. Okay? Alright. And taking into consideration that the value of z at omega 1 is 0, the resonance is obtained where tan beta L plus BC equals 0, and actually the value of BC itself is z naught omega c. Alright, so it is required to obtain the first derivative of z with respect to beta L. We are going to take the derivation of this equation or even of this equation. This is equivalent to this. Actually, this equation is simpler because this term is constant with respect to beta L. So we are going to take as minus j z naught over z naught cotan beta L, which is actually minus j cotan beta L. So it is required to find out the first derivative of cotan beta L with respect to beta L. The derivative of cotan beta L is minus sec square beta L over tan square beta L. And we have already minus, so this would be j sec square beta L over tan square beta L. And sec square can be represented as 1 plus tan square beta L. So dz over d beta L is 1 plus tan square beta L over tan square beta L. And actually from the resonance we know that at omega 1 tan beta L equals minus BC. So we can replace tan beta L by minus BC. So this minus BC squared would be plus BC squared. Here minus BC squared would be plus BC squared. Alright? And actually, we say that the value of VC is usually very small value because the capacitance is very small value. So 1 plus very small value, it can be approximated as 1. So dz over d beta L at omega equals omega 1 is nearly J over BC squared, assuming that BC is very small than 1. Now we have this term. D beta L over d omega can be obtained for the case of transverse electromagnetic line as L over VB. How comes? Actually, the value of beta is omega over the phase velocity, omega over VB. So this omega over VB multiplied by L, if we are taking the derivative of d omega L over VB by d omega, it would be L over VB. So now we have the value of d beta L over d omega equals L over VB. And at omega equals omega 1, the value of L equals by VB over omega 1. How comes? Effectively, as we mentioned, omega 1 will be close to the frequency when beta L nearly equal by, when we said that the value of L is nearly lambda over 2. So beta is omega over VB. This means that at omega 1, L is nearly equals by multiplied by the phase velocity over omega 1. So we can replace the value of L here by V phase over omega 1, then over V phase. So the only term of d beta L over omega, it would be simply by over omega 1. Now we have dz over d beta L is J over BC squared multiplied by d beta L over d omega, which is pi over omega 1. So this term completely, it can be replaced by J pi over omega 1 BC squared. J pi over omega 1 BC squared. And the remaining part is omega minus omega. This actually the input impedance of the coupled resonator close to the resonant frequency omega 1. Z as a function of omega would be nearly J by multiplied by omega minus omega 1 over omega 1 BC squared, where BC is Z naught omega C. If we note, all these calculations are assumed that the resonator is lossless. What will be the situation if we have small losses in the resonator? If we have small losses in the resonator, we can replace omega 1, the resonant frequency, by the complex omega, which includes the quality factor of the resonator. So for high quality factor resonator, or for high quality factor resonator, losses can be included by replacing the resonant frequency, which here is omega 1, by the complex resonant frequency. Assuming that the resonant frequency is called omega naught, the corresponding complex frequency is omega naught multiplied by 1 plus J over 2 Q naught, where Q naught is the unloaded quality factor. So we are calling the resonant frequency here omega 1 not omega naught. So instead of omega 1, we are going to replace it by omega 1 multiplied by 1 plus J over Q naught, where Q naught is the unloaded quality factor of the resonator. Doing this, we can obtain the input impedance for slightly lossy resonator as Z as a function of omega, it would be J by omega minus this combination over omega 1 BC squared. In the denominator, we are going to call it omega 1. But in the numerator, we are going to call it omega 1 multiplied by 1 plus J over 2 Q naught. So the first term corresponds to actually this term directly. The second term, it would be J omega 1 over 2Q. So J multiplied minus J, and we have negative sign, minus J multiplied by J, it would be 1 by multiplied by omega 1 over omega 1. So this would be eliminated with omega 1, J by over 2Q. So J multiplied by minus J would be unity. We have Y over 2Q naught BC squared. Actually, this is J multiplied by minus J by omega 1 over 2Q naught omega 1 BC squared. And omega 1 is eliminated with omega 1. J multiplied by minus J is unity. So the real part is pi over 2Q naught BC squared. And the imaginary part is exactly the same as the previous one. Now we have included the effect of the losses from the quality factor or the unload quality factor of the generator. And once we included the effect of the losses, we obtain in the input impedance a real part. And actually this real part corresponds to the losses part in the resonator. So this is the input impedance of the coupled resonator in this case, or the input impedance from the feeding transmission line coupled to the resonator. We have real part and imaginary part. And it should be noted here that this input impedance is normalized. This is normalized with respect to Z0. So this is the value of R, and this is the value normalized R, and this is the value of normalized JX. Okay. So finally, we have the input impedance of the coupled resonator is pi over 2Q naught BC squared plus J multiplied by pi omega minus omega 1 over omega 1 BC squared. As I mentioned, the corresponding resistance here R would be this real part multiplied by Z0, because this is normalized impedance. So the value of R is Z0 multiplied by pi over 2Q naught BC squared. For critical coupling, the input resistance should equal the value of the characteristic impedance of the feeding transmission line. So for critical coupling, R should equal Z0. This means that this value should equal unity, or in other words, the value of BC, the required of coupling, which is Z0 omega C. Actually, the value of C here depends on the spacing between the feeding transmission line and the coupled resonator. So the value of the required BC in this case should be equals square root pi over 2Q naught, such that this term would be unity. On the other hand, the coupling coefficient, it can be defined as, because here this is series RLC circuit, the coupling coefficient G is Z0 over R, as we mentioned in the previous video for the case of the series RLC circuit. And the value of R is Z0 pi over 2Q naught BC squared. So the value of the coupling coefficient G is simply 2Q naught BC squared over pi. If the value of G is less than unity, the resonator is undercoupled, and this condition it would be satisfied if the value of 2Q naught BC squared over pi is less than unity, or in other words, the value of BC is less than square root of pi over 2Q. On the other hand, if the value of BC is greater than square root pi over 2Q, then the value of the coupling coefficient would be greater than unity, and in this case, the resonator would be overcoupled. This is how to excite lambda by 2 printed line resonator bicapacitively coupled to microstrip line, a feeding microstrip line. All right? Okay.